Today's lesson is on minimization problems and the duality. In order to solve minimization problems, we first need to know how to transpose a matrix. Transpose means to interchange the values in the rows with the values in the columns. For example, if we have A equals the 3 by 3 matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're trying to find A transpose, notice we have an A with like what looks like an exponent of t. That means A transpose. We're going to interchange the row with the column. So the first row, 1, 2, 3, is going to become the first column, 1, 2, 3. The second row, 4, 5, 6, is going to be the second column, 4, 5, 6. And then the third row in A is going to be the third column in A transpose, 7, 8, 9. Notice that the size of A is a 3 by 3 matrix, and the size of A transpose is also a 3 by 3 matrix. But what happens if we try matrix B, which is a 2 by 4 matrix? If I interchange the rows, which there's 2 rows, with the columns, and there's 4 columns, A transpose is going to be a different size. So 4, negative 7, 3, 1, which is the first row of B, is going to be the first column of B transpose. 4, negative 7, 3, and 1. The second row, negative 2, negative 8, 5, and 6, is going to be the second column in B transpose. So notice that the size of B transpose is actually a 4 by 2. That's because the rows and the columns switch, and so therefore their sizes are going to be different. The next thing we need to know is the standard maximum form and how that is different than the standard minimum form, because the standard minimum form is what we're going to be working about today. What we have already done in the previous section is standard maximum form. So a linear programming problem is said to be in standard maximum form, and this is from the previous lesson, if condition 1, the objective function is said to be maximized. Condition 2, all variables are non-negative. All x sub I are going to be greater than or equal to 0. Now the I means it could be anything, x sub 1, x sub 2, x sub 3, any x sub any index. Condition 3 says all remaining constraints are in the standard linear form. A sub 1, x sub 1, plus a sub 2, x sub 2, plus a sub 3, x sub 3, plus dot dot dot, plus a sub n, x sub n is less than or equal to b. Now that was the conditions that we already dealt with in the maximum form. Let's take a look at the minimum form and see how it's different. The first condition is different because it says the objective function is said to be actually minimized this time, not maximized. Condition 2 says all variables are non-negative, which is the same as the condition 2 for the maximum. And condition 3 is a little bit different because all remaining constraints need to be in the standard form, linear form, a sub 1, y sub 1. Notice that's different because we're using y variables instead of x variables for minimizations, plus a sub 2, y2, plus a sub 3, y3, plus dot dot dot, a sub n, y sub n. The other thing is different is the inequality is greater than or equal to b. So the constraints have to be greater than or equal to be able to find a minimized value. So note the differences in conditions 1 and conditions 3. Condition 1, the objective function is either maximized or minimized depending on which one we're working on. And in condition 3, we are using x variables instead of y variables or vice versa. And the other thing is different is the inequality is the opposite sign. So as long as it's in the standard minimum form, we're going to be learning how to solve those types of problems today. Additionally, their objective functions have similar forms for the maximization and the minimization problems. So for the maximization problems, in the past we've used z equals and then c sub 1, x sub 1 plus dot dot dot, any of the other values. Whereas in the minimum objective function, notice we're using w instead of z. And also we're using the variables y instead of x. So those are some of the differences between the standard maximum form and the standard minimum form. Next, we're going to be talking about the duality. There's an interesting connection between standard minimization problems and standard maximization problems. It turns out that any solution of a standard maximization problem produces the solution of an associated standard minimization problem, and vice versa. Each of these solutions is called a dual of the other. Next, we're going to go through the steps to find the dual maximization problem from a minimization problem. We know that there's a connection between these two and they have the same solution. If I can change my minimization problem into a maximization problem, and I already know how to solve maximization problems because I did that in the previous section, I'm basically changing a min problem to a max, and I can solve it in the same way that we solved the other problem, which reduces our new problem to something we've already done before. So our steps there are: step 1. Without considering slack variables yet, put the coefficients of the minimization problem into an augmented matrix, and then put the coefficients of the objective function in the last row, not the negative of it, okay? So not the negatives. We're not solving for z or w in this case. We're just putting them in the bottom row. Then I want you to transpose a matrix, and then you can rewrite it as a maximization problem. So here on the next page, I'm going to try to leave my steps up here. Step 1, this is my minimization problem. Notice I have y variables and I'm minimizing a w. Okay, so what I'm going to do is I'm going to put it in a matrix right now. I have 3, 5, and 15 for the first constraint, 4, 7, and 20 from the second constraint, and the minimize objective function is going to go in the bottom. Notice this is not the negative, so I'm just going to put a positive 6, a positive 10, and we put a 0 for the last value because we don't have a constant in that minimized problem. Notice I didn't have a W column and I don't have any slack variables right now. This is just put the values in, okay? And I'm going to call this A. Next, step 2 says find the transpose. So I'm going to take A and find its transpose. So the rows become the columns and the columns become the rows. So the first row in A, 3, 5, 15, is going to be the first column in A transpose. The second row, 4, 7, 20, is going to be my second column in the transpose. And the last row, 6, 10, 0, is going to be my last column. So now that I have the A transpose, I can rewrite this in a maximization problem. So the bottom row is going to be my max problem, so my max objective function. So instead of w equals, I now have z equals, because this is a maximized problem, 15, and instead of y1, these variables in the blue are y1 and y2. So now the variables in the green transpose are going to represent x1 and x2. So now I have 15x1 plus 20x2 for the maximize objective function. The constraints are now going to be 3x1 plus 4x2 is less than or equal to 6. 5x1 plus 7x2 is less than or equal to 10. Notice before they were greater than or equal to, and now they're less than or equal to, because in the standard minimum problem they have to be greater than or equal to. In the standard maximum problem they have to be less than or equal to. And we also have x1 is greater than 0, x2 is greater than 0. These are requirements, these are condition 2 that have to be met for both max problems and min problems. Alright, so this is our new problem. And if I were, I'm not going to actually solve this for this example just yet, but if I were to solve it, I could then solve the dual minimum problem. So I've changed my min problem to a max problem. They have the same solutions, so then I could potentially get the answer to my min problem. And that's kind of the gist of how we're going to be solving minimization problems.